Hello everyone, my name is Byung Chul Yeo. I'm going to talk my poster briefly for FedAI conference. To begin with, I'm going to tell you the introduction part. For designing novel materials, it is very important to characterize crystallographic interfaces in synthetic materials. In particular, from the output images of STM, which stands for Scanning Transmission Electron Microscopy, we can assign interface structures. So far, STM datasets are being massively accumulated. However, we cannot fully exploit them. So we developed new automatic analysis tool by using artificial intelligence. And I'm gonna tell you how to automatically identify key features of crystallographic interface from STM dataset. Here is one of the STM data. At first, a sliding window scans entire image and extracting the patches at various positions like this. And these patches are represented in suitable way, for example, electron diffraction pattern or atom resolved image. And then they are sent to the machine learning models in order to identify key features. And finally, we can obtain identification map that has corresponding key features of local regions. To make it possible, we developed two independent models. At first, there is neural network model to classify crystal structure and lattice plane of local regions. In this case, the input is either FFT HADAF or CBED image. Second, there is regression model to identify rotated angle and lattice constant of local region. In this case, the input is HADAF image. And it is necessary to automatically and robustly recognize atom columns because we use the descriptor as the relation between atom columns inside the image. And let me explain the result of my research. For training and testing our models, we used simulated STM dataset that is about 25,000. So we confirmed that our model performance achieve perfect or nearly perfect classification like this. And next, we apply to the polycrystal structures. So here is the polycrystal structures that I used in left figures. There is 4 different crystalline regions, and 3 regions belongs to trained classes, and the other one belongs to untrained class. And using our models, we obtained classification map like this. As you can see, FCC001, BCC001, and HCP001 are predicted perfectly. However, the diamonds cannot predict because the neural network doesn't know about the diamond class. So how can the model check whether the output is misclassified or not? For this, we used Bayesian neural network. The Bayesian neural network means that it uses a particular weighting parameters on probability distribution in testing phase. So even output is not particular value, but distribution form. Anyway, using this model, so we estimate uncertainties. So as you can see, the uncertainty maps, only diamond regions have the high uncertainty values. It means that the high uncertainty values tell us that the classification is probably wrong. So using this method, we can figure out various uncertain crystal regions, for example, unknown class or defected structures. And next, we apply to the experimental data And here is the experimental images and corresponding classification map in left figures. And using our models, we can figure out the key features of local regions and even the location of grain boundaries. In summary, we developed new automatic analysis tool in order to identify the crystalline interfaces. In the future, we expect that our models will be able to pave the way for self-driving microscopy. So thank you for listening to my talk.